Hello and welcome to today's chemistry vlog. Today we'll be diving into the topic of chemical kinetics. Chemical kinetics is the study of rates of chemical reaction. It is the changes in the concentration of reactants and products with time. Today we'll be conducting an experiment where we will be investigating the reaction between blue food dye and hydrogen peroxide in the presence of a base.
For our materials, we use the following: a mortar, beaker, graduated cylinder, sodium carbonate or Na2CO3, water, 3% hydrogen peroxide, a red cloth, blue food dye, and a smartphone with the color analyzer app installed. Initially, we need to determine the amount of sodium carbonate required to be added to the water to create a 100 milliliter solution with a concentration of 1 molar of sodium carbonate. To achieve this, it is crucial to understand that the formula for 1 molar concentration is 1m equals 1 mole per liter. Given that the desired solution is 100 milliliters, which is equivalent to 0.1 liter, the amount of moles in grams of sodium carbonate should be divided by 10. Firstly, we need to calculate the molar mass of sodium carbonate, or Na2CO3, where Na2 equals 22.9897692 times 2. C equals 12.011, and O3 equals an estimate amount of 16 times 3. Adding these values yields an estimate of 106. Dividing this by 10 and rounding results in 10.6 grams of sodium carbonate. Next, to determine the amount of water required, we refer to the density of sodium carbonate, which is 2.54 grams per milliliter. Using the formula P equals M over V, or P equals mass over volume, the volume of sodium carbonate is calculated to be 4.17 milliliters. Subtracting this from 100 milliliters provides the amount of water needed, which is 95.83 milliliters. Upon completion of these calculations, we are left with the 1 mole solution of sodium carbonate in the beaker. The subsequent step involves filling another clear beaker with 100 milliliters of distilled water. Following this, using a 10 milliliter graduated cylinder, 10 milliliters is extracted from the 100 milliliters of the 1 mole sodium carbonate solution prepared earlier. Then, using another 10 milliliter graduated cylinder, 10 milliliters of 3% hydrogen peroxide is measured out. Next, a stand is set up and a smartphone with screen recording and the color analyzer app open is positioned on top of it. The bottom of the stand is covered with a red cloth on which the beaker containing the 100 milliliters of distilled water is placed. Subsequently, the remaining 10 milliliters of sodium carbonate solution and the 3% hydrogen peroxide added to the beaker with distilled water. Then, blue food dye is introduced into the same mixture and stirred. An additional smartphone is placed beside the setup to record the time. While the smartphone on top monitors the RGB changes every 15 seconds, this monitoring starts when the red value in RGB exceeds 8, signifying the gradual loss of color in the blue dye and the solution's return to its original color.
Now let's go over all the final answers that we got. And since the required volume of the 1 molar solution is 100 ml rather than 1 liter, adjustments are necessary when calculating the mole quantity of the sodium carbonate or the NO2CO3. More specifically, the answer received using the formula needs to be divided by 10 or multiplied by 0.1. For calculating the molar mass of sodium carbonate, the following values are considered. Na2 equals 22.9897692 multiplied by 2, C equals 12.011, and O3, which is equal to 15.999 times 3. Adding up all these values, it yields 105.98753856. which when divided by 10 and rounded up, results in 10.6 grams of sodium carbonate. Next, the researchers need to determine the volume of water required. Since the density of Na2CO3 is not 1 gram per mole, a calculation is needed to ascertain the necessary amount of water to add to the 10 millimeters of Na2CO3 extracted from the 100 milliliter of solution. Using the formula density equals mass over volume, the formula is rearranged to volume equals mass over density. Substituting the provided data, volume equals 105.98753,856 grams of Na2CO3 over 2.54 grams per mole, or the density of Na2CO3, which yields 14.7. And by subtracting this from 100 ml, it provides us the required amount of water, which is 95.83 ml. As depicted in the table, the initial 5 minutes of the experiment remain constant, with reaction commencing about the 5-minute mark. A trend further elucidated in the figure detailing the time versus RGB, or figure 2.8. During this period, the blue dye began reacting with the hydrogen peroxide, as evident in figure 2.4 to 2.7, which are pictures of the dye turning blue, or less blue. This process only starts at the 5-minute mark due to a slight over-application of blue dye drops into the solution. In figure 2.8, or the red RGB versus time, the first graph illustrates the R value of the solution, while figure 2.9 represents absorption over time. Figure 2.8 demonstrates an upward trend, satisfying an increase in the R value as absorption declines, indicating a reduction in available reactants over time. Figures 2.8 2.9 reveals that reaction commenced around the 5-minute mark, serving as the baseline of both figure 2.10 and figure 2.11, which are the ln abs and the 1 over abs. Moreover, it is evident from figure 2.8, or the RGB over time, and 2.9, or the or 2.9, which is the graphs of absorption over time, that the R value of the solution increases, absorption decreases. The higher the R value, and the lesser the absorption, the more the blue dye is slowly being removed, and the solution turns back into its original red color from the red background. To ascertain the reaction order, the researchers employed in ln abs and 1 over abs analysis. When ln abs yields a negative slope, it indicates a first order reaction, wherein a positive slope, 1 over abs, signifies a second order reaction, with the slope representing the rate constant of the reaction. Thus, based on the result, it is evident that the blue dye exhibits a first order reaction.
Conclusion and recommendation. Overall, the experiment is a success, as it shows that as time progresses within the reaction, the R value representing the product increases, while the concentration of the blue dye reactant decreases due to the inverse relationship between absorption value and R value. Despite both reactants and products undergoing change during a reaction, the rates of change are not always equal. Initially, reaction occurs rapidly because of the high concentration of reactants, but as they are consumed, the reaction rate diminishes. Therefore, a higher initial reactant concentration results in a faster reaction. Understanding this phenomenon is crucial for controlling reactions and determining the optimal reactant concentration for achieving the fastest reaction rate. Preparing solutions can be challenging. In the initial phase of the experiment, a 1M solution was created using Na2CO3 and water, which was combined with 3% hydrogen peroxide and additional water. Obtaining the precise quantities of materials required considerable time and patience, particularly due to the need of small amounts. This phase underscored the importance of using accurate measuring tools, as inaccuracies could pose hazards, especially when handling chemicals in the laboratory. Table 3 presents some unexpected drops in value, which can be attributed to the researchers' utilizations of a free version of the Color Analyzer app. This app contains built-in software that may not be precise and can conflict with the smartphone's native camera software. Consequently, The researchers recommend employing better equipment and compatible apps, including a place with good lighting, and ensure more reliable and accurate results.